Hi, everybody who's just joined. We're just going to give it, I think, 1 or 2 more minutes, and then we'll get going. Okay, I think that we will get started. We have 4 presentations to work through, so I want to make sure we maximize the time. Good morning, good afternoon, everybody. Welcome to another UG2 webinar. This is actually the 20th in the webinar series. And we met as an early career sub-focus group and decided that it was time to really spotlight the amazing work that some of the early career scientists are doing within the glider community. So we're hoping this will become a recurring series, and we'd love your feedback afterwards to see how this goes and if you're interested in hearing more from that early career demographic. And next slide, Cassie. As always, I just like to give a shout out to the steering committee that works behind the scenes. We meet fairly regularly to go through different activities we need. We are still working through some action items from the workshop last year. And of course, we are gearing towards starting our planning for the workshop next year. So big shout out to all of these folks here listed. And just to let everyone know, there has been a slight change. Carl Goldman, who was the director of IUS, did retire at the end of April. So Kathy Bailey has stepped in to sort of take his place within the steering committee role. Next slide. Just a brief agenda for today. I have a couple of updates for you all, and I'll just take a few minutes to do those in a moment. As I said, we've got 4 great presentations. Well, Joe has helped select some great speakers spread around the country and working on a range of different topics to keep this really interesting. So very excited and grateful for those speakers to be so willing to present today. Next slide, Cassie. So as always, I just want to highlight some of the updates and upcoming events. So of course, the biggest thing, we did release the save the date for the UG2 2026 workshop, which will be held in St. Pete, Florida, and hosted by USF. That is scheduled for next May. And we usually have been having our workshops in September, but of course, hurricane season, we take that into account when we head to that area. So this one will be in May. We are just beginning some of the planning phases for this. And as always, if anyone has any topics they want covered or wants to run any breakout sessions or any ideas, we do really welcome those. So please always feel free to put something on Slack or send an email. We likely will be sending out some surveys to the community in the coming months, because as always, we want to make sure this workshop is useful to you and that you can come and get the most from that. A few other events happening. We did have a town hall abstract accepted for Oceans MTS, which is in September of this year, being held in Chicago. And this, we are focusing on piloting tips and tricks. So this was definitely something that came out of our workshop, was really providing more platforms for pilots to kind of meet and discuss tips, tricks, challenges, lessons, and so on. So very excited for this. And I do have a request. If anyone is planning on attending, and would like to be on the panel and offer some of these tips and tricks, please do reach out to me. We are seeking panelists who are very willing to be up there in the spotlight. Last week I did submit a town hall abstract in collaboration with EGO, which is the European counterpart to UG2, which is focusing on underwater gliders in action, ocean emergency preparedness. So we are going to co-facilitate this session and really highlight using gliders for emergency preparedness and crises on both sides of the Atlantic. So the US side, we're going to really highlight some of the amazing work that is being done for hurricane awareness, preparedness, and tracking. So we're crossing our fingers that that's accepted. And as soon as we know, I will share that with everybody as well. And then, as always, all of the documents, so the last workshop report and other documents, are available for download via the website. Next slide, Cassie. Great. That's enough from me. I'm really excited to jump into our presentation. Joe Gradone, who is the leader of our early career subfocus group, and he is going to help facilitate and moderate this session. So I will pass it over to you, Joe.
Cool. Thanks, Georgia. And hi, everyone. I'm your Vanna White for the day. And I'll just jump right to it. So first up, we have Frank Mcquarrie. He's a PhD candidate at the Skidaway Institute for Oceanography, studying coastal soundscapes using gliders as both passive and active acoustic platforms. He's defending his dissertation in June and hopes to continue his research in oceanographic engineering. So for anybody looking for an awesome postdoc, reach out to Frank after this exciting talk. Take it away, Frank.
Hey, I appreciate you, Joe. Hey, everyone. My name is Frank Mcquarrie, and I'm talking about modeling the high-frequency soundscape using glider data. I know a lot of us work in acoustics or have worked with acoustics, and so I'm just warning you, high frequency, I'm talking above 50 kilohertz, so far past what we can hear, and I'm working with telemetry data. I'll talk about why that is. Excellent. I'm going to give an abbreviated background on some underwater acoustics and past modeling efforts. I'll talk about our environment and some of the modeling I've done and why you should care. Excellent. So acoustic telemetry is using sound to relay information across open ocean. So this is whether you're tagging a fish to know, is it staying on the reef? Is it leaving the reef? Where is it migrating on the eastern shore? Where is it going? You can use instruments for that. For more transmitters, you can use gliders as receiver platforms. It's a mixture of whatever you want. Your creativity wise is the only thing that stops it. The problem is sound travels differently in different environments. So that's where gliders come in, is because changes in sound speed control sound propagation. On the right is kind of like I'm adding temperature and salinity equals sound speed. Pressure and depth also have a control of that, but not in 20 meters of water. We're in the South Atlantic Bight, so 20 meters is about our limits. Temperature is the biggest driver. So if you've ever swam in a lake or felt that stratification, that significant change in temperature with depth, that is what we're talking about. Sound refracts away from that. And so gliders are perfect because if we just had a boat with a receiver on top, we might not hear a tagged fish at the bottom of that ocean. But gliders can go above and below that significant gradient, profiling both. That's helpful for us if we're trying to listen for where is this fish. We know that that tag, that acoustic transmission is not traveling as far as we thought it might. The original modeling effort was for the NSF Smart and Autonomous Systems project. So this was a collaboration with a few other universities and groups. Our mission is to use robots to search a region for tagged fish. It sounds easy enough, but the problem is what I was talking about with that range at which we can hear these fish. We need these robots to go out and they themselves have to set their detection range. If I'm searching an area, how far am I actually searching? Am I looking straight down at the ground? Am I only searching the surrounding area? We've learned that at different times of year, we could be searching 100 meters reliably, and other times of year, we can reliably hear signals 500 meters away. That's a very significant difference if we're trying to be as efficient as possible. So that's what I'm working on. That was my part of the project, was creating that environment to work in. Previous model was as simple as possible. This was 5 years ago, when a glider surfaces, I want it to model sound as quickly as possible. And so that's using one glider profile. So a glider it goes down, comes up. I average the salinity, the temperature, and the depth profile from top to bottom and model it as simple as possible. So that's a flat surface. That's a bottom that's perfectly flat and it's a vacuum. So whenever sound touches it, it disappears, and one static sound speed profile. This worked rather well. So to explain, on the right, I have that thin column. On the left, that's our sound speed profiles. So that is from the top of the bottom to the water column. That's a measure of how sound is going to travel. In March and April, you see there's some significant stratification. Sound bends away from that significant stratification, that gradient, and that's going to change our coverage. So it's very heterogeneous. If we had some sort of boat or some sort of receiver on the top of that water column, we're not going to hear that tagged fish, even if we're right on top of it. If we have a glider, it can go above and below. So it's very helpful for us. In November, it's more homogeneous. There isn't that gradient, and so sound travels and there's more homogeneous coverage. It's a beautiful rainbow. The bottom is what I call beam density analysis. It's just quantifying the number of pathways between transmitter and receiver. Very simplified. We're trying to get better at that. The next steps include our environmental context, our signal strength, and background noise. Because on the right, it's just physics. It's just passing a line through A to B. The problem is that line is weakening as it travels. It's attenuating, it's losing energy. That is where I come in. That's the environmental parameters I'm going to introduce and talk about how I'm improving these models. So as a aside, why does background noise matter to telemetry users? So if you think about the best teacher you've ever had, if she had a classroom full of people talking, it's still tough to get that message across. That is signal to noise ratio. We need our signal to be stronger than the background noise. And so Innovasi/Vemco has defined this for us. For acoustic telemetry efforts, a challenging environment means very few, if any, detections are expected. Moderate says that detections are expected, but there's a reduced detection range. That's because as this sound travels, it's weakening. You can hear it closer and closer. You're losing range as it attenuates. And finally, optimal, many detections are expected. This is quiet. This is a lake. Gray's Reef spends most of its time in a challenging environment. They say it works great unless you're in challenging. We're dealing with that because of those little benthic invertebrates on the top right. That is a snapping shrimp. If you've ever dove anywhere near Gray's Reef or anywhere in that tropical or subtropical, you may have heard them. It sounds like oil in a pan. And the edges of our hearing go up to about 20 kilohertz, but those snaps go all the way up to 200 kilohertz. So we're one of the few animals that create noise. I don't know how loud this is going to be for headphone users, so I'm just going to play it a little bit. It almost sounds like there's a graininess to my microphone. It's just that snapping sound. So many times per second, we're dealing with this, and that's interfering with our signals. So I'm experimenting with a unique environment. I don't just have sound waves from A to B. I'm dealing with loud and quiet environments. And there's a lot going on in this figure, so I'll break it down. That top row is just wind events in February of 2020. This is from a buoy on the surface. I'm just tracking when and where there's large amounts of wind. The middle, the red, is a loud environment, and the black is a quiet environment. Yeah. So you can see that when wind increases, we're getting a lot of detections in our loud environment, and we're getting none in our quiet environment, and vice versa. That noise interference at the bottom is showing that red is far above that 650 challenging area. Unless wind is blowing, we're not hearing much in our loud environment. And I'm just squaring off a few of those sections showing that we're getting an inverse relationship. It's definitely more complex than wind good or wind bad. Excellent. For modeling sound transmission propagation, we have our initial priority was as quick as possible. Within a minute and a half of being at the surface, I want a glider to tell you how far away it can hear signals. We're now adding to that. My current priority is using glider data, that's the CTD profiles, and passive acoustics. If it's got a hydrophone on it, I can tell how relatively high or low that background noise is. So some of the model parameters I'm going to hand wave because I only have 15 minutes. We changed bathymetry to be flat, linear, or realistic between transceiver pairings. I modified the sound speed stratification for strength and depth and changed the surface waves for propagation. One parameter I added that I'm excited about is surface bubble loss. So on the left, these are not my pictures. It was surprisingly tough to get pictures on the Beaufort wind scale, but you can see that bubble layer forms. So as wind blows, The waves form, they crash, and there's a layer of bubbles at the surface, and that attenuates sound. That weakens any transmissions or sound that comes in contact with it. Because otherwise, if it's a flat ocean, it's almost a perfect reflectance because of the density difference. So especially at higher frequencies, anything that comes in contact with that bubble layer attenuates rather quickly. The formulas are on the bottom. I can talk more about that in questions if you're interested, but the threshold is 6 meters per second because around 5 or 6, that's when those whitecaps start forming. I'm not modeling the depth of that bubble layer. I'm only using it as a measurement of attenuation whenever signals come in contact with it. So the bellhop ray tracing on the left is very simplified inputs. I'm throwing in a sound speed profile from a glider or from modeled, whatever I want, bathymetry between the two instruments, and then I'm modeling 1,000 rays through that environment. That's a new metric, is the signal strength. So on the x-axis is arrival time. I'm not doing too much with this because a Novacy is pretty good at when it hears one ping, it correctly ignores all the echoes because of a blanking period that I can talk about if questioned. But on the y-axis is signal strength. You can see the ones that are going straight from A to B are the strongest. They're not attenuating at the surface or the bottom. That's important going forward. So original, I just looked at rays traced. I just looked at pathways, which is, I mean, it helps, but that's saying that, in November, there's a 5% chance of hearing it 2,000 meters away. That's not realistic. So I needed to bring in signal strength. So as those pathways arrive, how powerful are those signals? And can we hear them? So that's why I'm saying best is detectable pathways. I'm not only measuring attenuation of these signals or how strong they are when they arrive, I'm also measuring the background noise for them. So yes, they're arriving at X strength. Are they above whatever the Y is, whatever that detection threshold is? I want to illustrate why that's important. So on the left is surface bubble loss on the X. That can be thought of as wind. So 0 is a calm, flat day. The surface is a reflector. And 15 is gale force. We're starting to hear plunging waves, very deep bubble layer, attenuating a lot. And Y is just arriving signal strength. So this makes intuitive sense, as the more surface bubble loss there is, the weaker our signals will be whenever they come in contact with the surface. A much more complicated answer is, instead of just looking at signal strength, I'm looking at detectability. I'm looking at the number of pathways that can actually be heard with the background noise, above the background noise. This still, we're getting way more detectable pathways with 0 bubble loss, but you can see it's more complex. It's not that nice linear relationship when purely signal strength is. This is where I'm bringing it back to that example I showed you in the quiet and loud environment having inverse effects from wind. So the static versus dynamic background noise. Wind forms that bubble layer at the surface. That weakens transmissions, so the signal strength is going down. But my hypothesis is that it also lowers background noise. And so in some situations, if it's already quiet, the lowering background noise doesn't help much, but the weakening transmissions will hurt you. That background noise creates that floor for detectability. If that's too high, we can't hear anything. So on the left is a static low noise environment. You can see that at 45 decibels straight, we're losing our signals. They're getting weaker. We'll go from 6,100 detectable pathways over all of our models down to 4,100. We're losing them because they're weakening when they're coming in contact with that surface bubble layer. In the dynamic noise, we start very loud. Like you can think about those snapping shrimp snapping in the background. You can't hear yourself think. We only have 1,500 as opposed to 4,700 when winds increase. So winds increase, we're thinking of large surface waves. We're looking at that surface bubble layer. That's going to be a problem for our signal strength. It's much weaker signals, but more of them can be heard because of that changing threshold. To do it more robust, I don't have the time to go into exactly how it works, but a generalized additive model is a great way to look at this type of data set. It's a statistical approach to analyze complex relationships between predictors, which are the environmental variables, and our outputs. So instead of just looking at a regression of one-to-one, does it go up with wind or down with wind? I'm looking at the relationship between the different effects of wind. Excuse me. So the formula is on the top right, and you can see like I have S and then something in parentheses. That's because it's slightly smoothed. I'm trying to push it into my model in a certain way with a certain degree of freedom. I do show that detection threshold and surface bubble loss are by far my strongest predictors of whether or not there will be detectable pathways, especially detection threshold. And these two are my inputs. These are things that I'm bringing to the table because before I can model sound from A to B. That's interesting. But unless you're thinking about attenuation and you're thinking about the resistance you're going to get from that environment, it's not as important. It's not useful enough for me. So another strength of the game is interaction terms. So instead of looking purely at how detection threshold or how surface bubble loss is affecting detectability, I can compare them both. I can say, okay, what about the effect of both of them combined? And that kind of elucidates the answer to our problem. It kind of answers our question a little bit better. So on the left is my quiet environment. The detection threshold's low. I've shown it in average, that little dashed line. The x-axis detection threshold. So you can think that can be thought of as background noise. So we're relatively low background noise with the y being surface bubble loss. There is a huge difference in no bubble loss versus high bubble loss. We're losing a lot of our detectable pathways in our quiet environment. In our loud environment, even if we're changing detection thresholds, even if we're going from 68 down to 58, there's still not as large of a difference between no bubble loss and large. And there's a huge difference in detectability as we change that detection threshold. So some takeaways: background noise acts as a floor for detectability. You can't just look at signal strength and you can't just look at pathways. You need to think about whether you need to use high power tags to be heard over the background noise or decreased expected range. I haven't brought up collision analysis, but that's something to consider if we're going with high power tags. It's a balance, a trade-off. There's also detectability in low noise environments. They're going to be hurt by winds. There's a lot of range testing papers out there that talk about how wind is detrimental to acoustic telemetry. I'm here saying that that's only in quiet environments. If you're in subtropical or tropical waters where you're expecting lots of benthic invertebrates, namely snapping shrimp, you need to worry about this. Glider data helps predict acoustic telemetry success, and they're very, very helpful. Originally, I thought it was just because we're using their profiles, but at this point, they seem like the perfect platform. We can put the receivers on them so they can directly account for those detections. They can go above and below the gradients. The hydrophones are measuring background noise, so we can set that detectability threshold. They're mobile and robust, so they can address spatial and some of the temporal concerns. I'm very impressed by them. I think they're going to be used more and more for these types of efforts. Time for questions, comments, or sincere compliments. I appreciate you.
Awesome job, Frank. I think we can allow for questions, just like if anybody has any comments, you can unmute and ask them or type them in the chat and I can read them. Either one works. That was super cool, Frank. Really unique talk.
What's the first one? They're shy.
I know. I'll get us started because I have one. So I'm wondering how computationally intense is it to do this type of work? Like, is this something that you could you just do shoreside, like that, or is it something that you've considered like packaging up and putting on the glider itself?
I've been thinking about this originally. It's very easy. Like the original beam density analysis is super easy because it's so simplified. With this, I was originally planning it from more of I'm planning an acoustic array and I'm thinking about how far away to place my receivers or transceivers, whatever your instrumentation is. As for on the glider, it certainly can. You need some sort of scaling factor for background noise. I know Jack might talk a little bit about PAMS data and that type of passive acoustic monitoring. I'd be interested. This isn't a problem. Like running this in the background, where is it? There you go. These models run, 2 seconds, 3 seconds long. If you have the bathymetry, if you have the sound speed profile. So glider comes up, it transmits data. As soon as it gets a glimpse of one of those yo profiles, it can easily do this, given you know your environment.
Any other questions? Then Frank's email's there if anybody has any questions they'd like to follow up with him about. But then maybe we will move on to our next speaker, and that is Turner Johnson. So I will introduce Turner. Turner is a PhD student at Scripps Institute of Oceanography who uses glider measurements to study upper ocean dynamics, working under the supervision of Dan Rudnick. Her research focuses on understanding the relationship between mesoscale mixing, submesoscale turbulent features, and the impact of larger scale heat transport and energy dissipation. So take it away, Turner. I am excited to hear from you.
Okay, hello. Okay. So just doing some Zoom. My name is Turner, and I am working with Dan Rudnick to study dynamics in the Western Pacific. Here, I'm starting out by showing a nice painting that a local artist has done of the Scripps Submarine Canyon, showing some flora and fauna, and also showing how to lose a spray glider by driving it deep into a crevasse. So I would not recommend piloting a glider like this, but just a nice way to start. So we're going to start with the grant, which is an ONR funded grant called ARCTURX, which stands for Island Arc Turbulent Eddy Regime or Regional Experiment. Singular guiding focus is to locate a strong eddy in the Western Pacific in this energetic NEC and STCC region. Here is a screenshot of a movie of a MIT GCM forecast, courtesy of Ganesh Gopalakrishnan, that shows the international waters in this light gray. It's kind of this this weird U or V shape is the international waters. He's also got in contour is sea surface height, and then he's also run an eddy tracking scheme to show, I believe, anticyclonic eddies in red and cyclonic eddies in blue. So this was used in order to locate the eddy. Another consideration is seen in this ROMS forecast, courtesy of Javier at Rutgers. Here you'll see the same international waters, and you'll see this very large blue track. This is actually the track of Typhoon Mawar, which in 2023, quick aside, was extremely destructive to Guam. It hit Guam right before becoming a Category 5 storm. And that was like a week before the Thompson was scheduled to go out and do this deployment. So it was this big issue. You can see it here from space. But namely, it kind of limited the region of study. And so the perfect eddy was not available. So I'll get into that more. The main goals with ARCTURX are to use underwater gliders, floats, and surface drifters to measure the eddy over the course of several months. And I'm going to be focusing on underwater gliders for this talk. Yes, the goals are to characterize the dynamics of the ocean region and eddy. And I want to stress that this was a big collaboration between UCSD, Oregon State University, University of Washington, and the National Taiwan University. Okay, so in May of 2023, these 11 gliders were deployed via the Thompson. I will confess that these photos, I was not able to go on the 2023 cruise, but I did go on the 2025 ARCTURX cruise, which also deployed all 3 types of gliders from the Thompson. So hopefully these are pretty accurate. It's just showing big collaboration and big thanks to the crew of the Thompson. So once the glider's in the water, I'm sure you're familiar with the spray method of altering its buoyancy so that it does these profiles to 1,000 meters over a length of 6 kilometers, which also takes place over 6 hours. And every 6 hours, it phones home via Iridium. Also shown is that the typhoon that they're trying to avoid. And so the spray gliders take data on the way up, and this data is then binned into vertical profiles. So what does the distribution of data that was taken look like? I've done some very vague matching up of latitude, longitude to show the tracks of 11 gliders. They focus in on that red eddy right there. And they do this wheel spoke pattern for a few months, and then in the last month, they are kind of forced to bug out to the Northern Marianas Islands due to some last minute political issues. And so once they are at the Northern Marianas Islands, they were recovered with the help of citizen scientists on fishing boats. In particular, Dan was mentioning the help of this fellow named Cecilio. And so you can see here, it's a pretty small boat to do recovery of an expensive glider on. Okay, so with the data, here, as I was mentioning, is the wheel spoke pattern. This is a temperature plot showing vertical profiles from all 11 gliders. These measurements are 4-dimensional in X, Y, Z, and time. And all of them are measuring temperature and salinity. The spray gliders are also fitted with ADCPs, so they have Doppler U and V, which I will get into. Keeping this brief, Dan has this method of taking sparse fine scale profiles and mapping them onto a uniform grid in X, Y, Z, and T. And so you kind of lose a bit of the fine scaleness, but you gain the ability to do more exciting math, like the full vorticity. And then he also uses this to calculate W via the omega equation. And so, yeah, this slice that I've taken in the section data is roughly equivalent to this, this latitudinal slice in the map. And then these 3 subplots on the right are showing the same. This is looking downwards, kind of in latitude and longitude. You see the same wheel spoke pattern, and the map is able to kind of extrapolate a little bit past using statistics where exactly the gliders were, but this shows 3 different depths. So I also want to talk about my quantity that I have been studying the past few months is the Richardson number, which is a way to measure the potential for diapicnal mixing through shear instability. And so we have n squared on the top and shear on the bottom. And so it's kind of this question of, will stratification dominate or will vertical shear dominate? And some of you guys might be familiar with the Kelvin-Helmholtz instability, which is a type of shear instability that occurs at Richardson of 1/4. I think that I'm also interested in opening that up to be a little broader Richardson value of around 1. So another hoop to jump through is that when things are very stable, Richardson number goes to infinity. And so that is a little difficult to plot. And so I've chosen to take the arctan of Richardson, which maps infinity onto 90 degrees or pi/2. And it maintains when Richardson is very small, it keeps that fidelity. So yeah, once again, low Richardson number is where interesting mixing is happening, and high Richardson number is where there's stable stratification. So looking at the 4 spray gliders, which have the velocity measurements, here are the top 300 meters of each of them. You can notice that there is a mixed layer depth of below 50 because this is the summer. And yeah, the gliders are profiling the eddy until just about late July, which I don't know if you can see my mouse, but it's kind of where this large mixed layer event is happening. And so, yeah, we know that there's instabilities happening in the mixed layer, but something that is interesting about these plots is that between 100 and 250 meters, there seems to be these little spikes and events of arctan Richardson happening. And so I'm trying to parse out what is happening here. Okay. So I start to look at the relationship between Richardson number and Rossby number, which is the vorticity normalized to the local Coriolis. And so we are able to calculate this from the objective map. And it is thanks to the objective map that we have this kind of interesting fun value. And so I'm plotting that directly against, I'm co-locating the arctan Richardson from the sections, the section data, with the Rossby number from the map. And so I'm just plotting those two vectors against each other in a scatter plot. Just to see, I'll talk more about their distribution, but the positive Rossby numbers where we see cyclonic events and negative Rossby numbers where we have anticyclonic events, which is separated by the dashed line. We can also see that there's this big tendency in arctan Richardson for stability. And so I am not interested in that, and I'm more interested in the unstable regions. And so kind of looking at this vertical distribution here in Rossby number, some possible hypotheses include frontogenesis, where small Richardson is associated with positive Rossby number, and the trapping of near inertial waves, where small Richardson is associated with negative Rossby number. I have some slides about the mechanisms of these, but I don't want to spend too much time dwelling on them. I think that the big picture is that at fronts, cyclonic features tend to dominate based on conservation of potential vorticity, and in line with frontogenetic theory. And this is based on a paper by, it's called Asselin and Young, by which negative regions of vorticity will trap near inertial waves, and they will propagate downward, creating mixing along the edges of eddies. So this is kind of like where there is anticyclonic vorticity, we would expect more mixing or smaller Richardson number. Okay, so here I've made a joint PDF. This one on the left is pretty much the same thing as the scatter plot as I showed you, but it is showing the density of the distribution. I've also looked at some other statistics like strain magnitude here. So that's why it is positive. And I'm also looking at a statistic that is a combination of these two, which is known as a Kubo Weiss, which is just the strain magnitude minus the magnitude of Rossby number. And it tells us whether the region is strain dominated or vorticity dominated. So I'm going to, oh yeah, okay. So next I'm going to separate out the statistics in Richardson space, which is here along the x-axis. And I'm separating them into 30-degree bins. So I will have the first bin is 0 to 30, then 30 to 60, then 60 to 90. And these are kind of parallel to like where we expect the most mixing, middle amount of mixing, and least amount of mixing to happen according to arctan Richardson. Okay, so I know this is a lot of subplots, but the first row is vorticity, the second row is strain, and the third row is a Kubo Weiss. And the columns are the 30-degree bins that I was talking about in arctan Richardson. So these are conditional PDFs that allow us to separate out what Rossby number, strain, and a Kubo Weiss look like in regions of high mixing. And so the most interesting thing to me here is where there is most mixing in low arctan Richardson regime, vorticity is pretty highly skewed. We almost see two distributions. This is subplot A. One that is negative with greater area under, and one that is positive. And so I'll talk about a tiny bit more about this. We also see in strain that the mean strain is higher for, there's kind of this like area under the curve in plot D that is not very present in plots E and F. And so there are just more high strain events in low arctan Richardson or high mixing zones than in stable zones or high arctan Richardson zones. I'm also including a Kubo Weiss, but this kind of a subject of further research. We can see here that it's there throughout all of the arctan Richardson bins. There's this high vorticity domination, which we kind of expect from having chosen an eddy. So yeah, my principal takeaway is kind of parsing out more of this distribution. And so, yeah, when we've conditioned Rossby number by arctan Richardson, which coincides with areas of, I call it shearly unstable mixing, it seems like two distributions in Rossby number appear. We have one that is many counts that are very slightly negative Rossby number, which I think is associated with anticyclonic events. And then we have fewer but stronger events that are positive vorticity. And so I kind of think that there's maybe a background, or not a background, there's some amount of near inertial wave that's kind of happening throughout the study. And then I think that there's kind of a front that like passes through the region. And yeah, I think that here the mixing is associated with frontogenesis. Future directions are plentiful. If I say that there are near inertial waves, I need to look at a spectral analysis and confirm that with frequency. And then also maybe with the drain piping effect, there could be vertical propagation. So I should look at W perhaps, which has been calculated. I also have these interesting figures that I need to sew in that are vertical heat flux from W prime, rho prime. And then I also have I'm interested in connecting it more to larger scale baroclinic instability and looking at Rossby number and horizontal buoyancy gradient strength. And of course, none of these have error bars, so I do strongly need those. But yep, that's it for me. Thank you. Any questions?
Oh, wow, Turner, that was really exciting and cool. You did a really good job of explaining a pretty complicated analysis. That's awesome. Any questions for Turner? I'll ask one. This is great. It's like I got my own special collection of seminars. So the map 4D mapping that you did, do you do that in the Richardson number too?
Yes, I have done it in Richardson number. The thing about Richardson number is that it happens on scales that are smaller than the objective mapping decorrelation length scale is. I have a slide here. The big choice in doing the objective map, which is kind of a type of model, it's like a statistical model, is that you pretty much choose how far the influence of features reach. And so we chose to do decorrelation scales in X and Y of 100 kilometers and in time of 20 days, because we were kind of looking at this big mesoscale eddy kind of on the edge of submesoscale. And so with a grid length of the grid spacing, which I also neglected to mention here, is 10 kilometers. It kind of feels like shear instability would not it doesn't show up when I plot it on the maps.
Yeah, cool. I was thinking of how that would you'd kind of gain confidence in that, and that answers my question. Yeah, really, really cool though. Any other questions for Turner? Okay. So thank you, Turner. And we will move on to our third speaker now. So next up, we have Alice Wren. So Alice is an incoming assistant professor at Arizona State University who will lead a lab based out of the Bermuda Institute of Ocean Sciences, BIOS, that we're all very familiar with, I'm sure. Dr. Wren has a PhD from Scripps and is currently finishing up a postdoc at Woods Hole. So take it away, Alice.
Okay, thanks. Just took me a second to get set up. So yeah, I also did my PhD with Dan Rednick, so this will be something else Dan is involved in, but in a bit of a different direction. So today I'm going to talk about seasonal dissolved oxygen gas exchange in the California current upwelling system. And yep, I'm finishing up at Woods Hole. I'm a postdoc with Robert Todd. But also while I've been here at Woods Hole, I got the chance to work with Rue Nicholson. And this work I started with Dan in my PhD, and with Rue I added a little bit at the end looking at gas exchange. But this was recently published in Progress in Oceanography, so I'm happy to share it with you today. Yeah. And this work was mostly supported by NOAA. Okay, so this is the outline of the talk. I'll just go through it really quickly. But our motivation is to study the seasonal cycle of dissolved oxygen in the central and southern California current system, and also study air-sea gas exchange, which is basically how oxygen leaves the ocean and goes in the atmosphere, or how the ocean absorbs oxygen from the atmosphere. And so we're going to do that using a network of underwater gliders. So in particular, the California Underwater Glider Network, which is run by Dan Rednick. And we're going to use glider observations from 2017 through 2021, so 5 years of oxygen. And I'm going to present basically highly variable dynamic seasonal variations in oxygen air-sea gas exchange. All right, so dissolved oxygen is important for marine life, and you can also use it as a tracer for dynamical physical processes. We know that climate variability in the oceans and also long-term change in the oceans can affect dissolved oxygen concentrations. And one of the goals of this California Underwater Glider Network is to monitor dissolved oxygen in the California current system. So as such, one of the first things that we want to be able to understand is the seasonal cycle. And in this region, there is a strong seasonal cycle that affects the concentrations of dissolved oxygen. One of the cool things that I think we're going to do is evaluate regional oxygen air-sea gas exchange from observations today. But also in general, this annual cycle of oxygen that we've created, we hope will inform regional and climate models. So I'll briefly introduce the California Underwater Glider Network. There are 3 onshore to offshore transects that are part of this network that I'll be talking about in the results today. So they're numbered 66.7, 80, and 90. This is because they correspond to the Cal Coffee Hydrographic Survey, which has these numbered lines as well. So 66 is off of Monterey Bay, California. 80 is off of Point Conception, California, and then 90 is off of Dana Point. So variables such as temperature and salinity have been measured since 2007 very consistently. And then in 2017, we consistently added dissolved oxygen as well. And I'll say one of the great things about this network is that there is almost always a glider on any one of these transects making an observation. And so we are able to resolve the annual cycle or what happens over the seasons of the year very well. All right, so we're using spray underwater gliders, the same ones that Turner talked about. And then in this California region, the spray glider is equipped with a Seabird 63 dissolved oxygen optode sensor. And that allows us to measure dissolved oxygen. But we were also very careful with the data quality of the oxygen. And so we published this paper in JTech describing our methods of a 2-point correction in the laboratory for the dissolved oxygen data. And in this recent Progress in Oceanography paper, we also describe our methods further. So I'll just point you to those. Because I'm going to make a calculation on air-sea gas exchange, the quality, the accuracy of the dissolved oxygen at the ocean surface is very important. So I'm just emphasizing that we paid attention to that in our data collection and processing. So what I'm going to do is just describe an annual cycle. And so we fit an annual cycle to our data using weighted least squares with 3 harmonics of sine and cosine. And this is very similar to the way that Dan Rudnick and Kasia Zaba created the annual cycle for the other variables such as temperature and salinity of the California Underwater Glider Network. So one thing that I'm going to add is this calculation of air-sea gas exchange. And then for this, we actually need to use an empirical formula. And all of the empirical formulae generally take 2 variables. So one is the surface oxygen saturation. So here we're getting that, here we're getting that from glider observations. And then they also take as an input the wind speed. So in this study, I've used just the NCEP North American Regional Reanalysis. So it's an atmospheric reanalysis that gives you what the winds are doing. And I'll just mention that the parameterization we primarily used in the study is this Liang et al. Parameterization. And it has been shown to work well in the polar regions, particularly because it includes the effect of bubbles on oxygen. And bubble dynamics were estimated via LES or a large eddy simulation model with these dynamics. But what we also did was look at 4 other parameterizations for air-sea gas exchange, which I'll also just say that air-sea gas exchange is the oxygen flux through the ocean surface. So what we also tested these other parameterizations, and in our study, they're all qualitatively the same. So in this region, it did not make a difference which one we used. All right, so now I'm going to start on results. So first, I'm just going to describe the mean state and just get you oriented to the domain that we're in. So these plots have depth on the y-axis, and then on the x-axis is our offshore distance. So the coast is always going to be on the right-hand side. I will just talk about the locations of these 3 lines briefly once again, but we have line 66.7, line 80, and line 90. And they're in 2 sort of regions of the California current system. So line 66.7 is in what's called the central California current system. In the central CCS, there's generally very strong seasonal upwelling with a very narrow shelf. And then line 90 is in what's called the Southern California Bight or the Southern California current system. And the winds are a little bit different. Upwelling is perhaps a bit milder. And there's also bathymetry such as ridges and islands that affect the circulation as well. And so then in between line 66 and line 90, we have line 80. And line 80 comes off of Point Conception, and it's pretty much at the boundary between the central and the Southern California current system. But line 80 often has a lot of characteristics of the central California current system. Okay, so now that we're oriented, the color contours on the plot are the dissolved oxygen concentration. And so red is high and blue is low. And you can see in these mean state plots that we have a very strong vertical gradient in oxygen. So the surface of the ocean is always highly oxygenated. That's because it's in contact with the atmosphere and it can equilibrate with the oxygen in the atmosphere. And then in the CCS region, we very quickly have lower oxygen conditions at depth. So the contour that I'm going to call hypoxic is the 60 micromole per kilogram dissolved oxygen contour. And we start seeing waters of that oxygen concentration about 250 meters depth at the coast. All right, so that's the mean. And I'm actually going to skip some of our other results and kind of really focus on the surface ocean. Oops, I keep having trouble with PowerPoint. All right, so this set of panels looks at the oxygen saturation at the ocean surface, which we're calling 10 meters. For us, it's a 5 to 15 meter bin, but that's our surface ocean. And in these panel plots, the month of the year is on the y-axis, and then the x-axis again, your distance from the coast. So this is the what happens in an average year, right? So I'm presenting to you the annual cycle. One of the first things that jumped out to me when I made these plots is that there's a lot of areas of pink, which is when the ocean is oversaturated, and a lot of areas of blue when the ocean is undersaturated. So it's not that this surface ocean is in equilibrium for the year. And in most of the space of these plots, it's either over or undersaturated. And the oversaturation occurs mostly offshore, and undersaturation is found at the coast in winter and also in spring and summer. So the first row is line 66.7 and line 80. These are, again, more characteristic of the Central California current system, but we see very strong undersaturation in spring and early summer, maybe 15 or 20% undersaturation. And then offshore of that, we have the light pink or the oversaturated waters. For the second row, this is line 90 in the Southern California Bight. And you'll see at the surface that basically for the entire year, the waters are oversaturated. But if you look a little bit deeper, so the panel D is at 20 meters, you can see that there are some spatial temporal patterns of oxygen undersaturation. So one of the big drivers of this pattern is the seasonal upwelling signal. So what I'm going to show is the same four plots, but instead of oxygen saturation, it's going to show potential density. So you can see, especially in that first row, line 66.7 and line 80, that we have dense waters that are found seasonally at 10 meters near the coast in the spring and summer. And if I flip back and forth, can see that they correspond well with those highly undersaturated dissolved oxygen waters. For line 90, again, we don't see dense, and in this case, dense is maybe 25 kilogram per meter cubed. We don't see that water at 10 meters. And so that also is consistent with us not seeing these strongly undersaturated waters at the surface. All right, so in connection with upwelling, one of the really remarkable observational results that we were able to make is that we find evidence of dissolved oxygen ventilation occurring seasonally. So this is the isopycnal 25.6, one of the deepest isopycnals that approaches the surface on line 66.7 and line 80 during the seasonal upwelling. And so in these plots where there's a little gray patch, that's actually where that potential density disappears. So when that isopycnal becomes part of the mixed layer and interacts with the atmosphere. So for A and B, this is the anomaly of oxygen on that isopycnal throughout the year. And then for panel C and D, that's the depth of the isopycnal throughout the year. And what we see is that the isopycnol, as it approaches the surface during upwelling season, is oxygenated. Oxygenated. But we also can see that this perhaps 20 anomalously high of about 20 micromole per kilogram dissolved oxygen concentration. We see that signal offshore and that it appears to propagate offshore as well, but we see this signal offshore and having a signature of about 5 or maybe up to 15 micromole per kilogram of higher oxygen than you would expect. And then if you look on panel C and D, once you get to 300 kilometers from the coast, that isopycnal is at 100 meters depth or lower. And so this is an example of the classic ventilation of the interior ocean on the edges by outcropping isopycnals. All right. That was all very exciting as a physical oceanographer, but now I'm going to go back to air-sea gas flux and mention that I basically focused in the last slide on this really cool phenomenon that originates from the upwelling right at the coast. But what's happening overall in this region? So panels A and B show the air-sea flux of dissolved oxygen, and red indicates oxygen going into the ocean. Blue indicates oxygen leaving the ocean. And you'll see that this air-sea flux of oxygen mirrors the pattern of saturation that we saw previously. So in those undersaturated waters, the ocean is gaining dissolved oxygen, and in the oversaturated waters, the ocean is ejecting that gas into the atmosphere. What you'll see if you integrate over this area and through time is that actually, if you do the calculation from the coast to about 400 kilometers from shore, this whole region is a net outgassing region for dissolved oxygen. The region that is a net uptake region for dissolved oxygen is only from 0 to about 100 kilometers from the coast. So even though you have this very strong signal of undersaturation at the coast, it is compensated by the oversaturation that occurs offshore. All right, so I'm going to summarize. One of the things that I think maybe is more of a result, but that I found striking is that the air-sea gas exchange on line 66.7 and line 80 in spring and summer, that the magnitude of that flux is reaches up to 50 millimoles per meter squared per day during the upwelling season. And this is actually the same magnitude found in the Southern Ocean by Seth Bushinsky et al. Using BGC Argo floats. So it's very, very strong, but also very, very localized. And so perhaps not surprising that we are then able to measure this oxygen ventilation of the ocean interior that comes from this upwelling that is occurring along the coast. Despite this, though, The Central and Southern California system is a region with net oxygen outgassing when you include this offshore region. And I didn't discuss it and the results here, but we believe that a decent portion of that is due to biological production of oxygen. And on our paper, we make an estimate of the contribution that's due to just seasonal heating and cooling. But their seasonal heating and cooling does not account for all of this oversaturation signatures. So we believe that biologically generated oxygen is also important here. All right, so oh yes, so only the near shore, about 100 kilometers in the central CCS, is an area with net dissolved oxygen uptake from the atmosphere. I was just gonna plug that I'm gonna start as an assistant professor. This talk was a lot of biogeochemistry, but I also do straight physical oceanography. So if you're interested in either of those two topics, I will be based in Bermuda, which is not too bad of a place to be, I think. And yeah, I'll take any questions. Again, the reference I put on this slide, and it was recently published in Progress in Oceanography.
Awesome, Alice. Really, really cool talk. Any questions for Alice?
I have one. I may have missed this. I am wondering how you calculate the oxygen flux. Is it in that surface 5 to 15 meters?
So yes, it's a parameterization with the basically surface saturation or undersaturation of oxygen. And also the simplest parameterization has something called like a transfer velocity, but it's almost like 1D fixed diffusion. So there's some parameter that tells you how fast or how much the flux should be, and then you look at the concentration difference between the ocean and the atmosphere, assuming the atmosphere is at 100% saturation, basically. Does that help?
Yep, totally. Great. Thanks.
And then I should mention that the other parameterizations also include lots of other things. So but that's the basic idea. Yeah.
Any other questions for Alice? I have one. So this is like a really cool, massive data set, right? I know you only had a short amount of time to talk, but do you see any trends in the oxygen data over this time period?
That's a great question, and I haven't looked at that, but I'm sure that Dan maybe has taken a peek at that. And this is definitely is like the last portion of my PhD, but there's definitely more to do with this data set. Definitely the next step is to look at interannual variability. Yeah.
Barring no more questions, last call, last call. All right. Thank you, Alice. And we'll move on to our last speaker. So Jack Slater is a glider engineer and master's student working in the Coastal and Polar Physical Oceanography Lab at the Virginia Institute of Marine Science. His research involves utilizing gliders as acoustic platforms and developing novel instrumentation techniques to advance glider research capabilities. So take it away, Jack.
Okay. All right. Hello, everybody. My name is Jack Slater, and I'll be presenting on our journey into adapting gliders for acoustic oceanography. So first I'll start by talking a little bit about our lab. So I work in the Coastal and Polar Physical Oceanography Lab at the Virginia Institute of Marine Science. This is our team here, and I've got a QR code up in the top right of our lab website. I'll also take this opportunity to talk a little bit about myself and how I got into gliders. So I was a physics undergrad at William & Mary with a concentration in engineering, and VIMS is owned by William & Mary. So I had an opportunity to intern in our lab with Dr. Gong, where I started working with the gliders. And then once I graduated, I was able to stay full-time as a glider technician and engineer, and started taking master's classes recently to sort of develop my so on the academic side. So over that time, I've had the opportunity to explore gliders both as a technician on the hardware side, as well as doing some of this research and seeing some of that glider collected data and how we can use that. And I'll go through both of those sides on this talk. So this is just an overview. I'm going to go into the motivation of why use gliders as an acoustic platform, which Frank touched on earlier. Then I'll talk about how we integrated a hydrophone system into our Slocum gliders, both a G2 and a G3, and where we plan to take that. And then I'll talk about our initial data analysis and where we're going to take that. So I'll start with the motivation. So why gliders? Like Frank said, they're super quiet, flat platforms. They have long endurance, and they can span over depth. So we can get these really good range-dependent measurements of the sound speed, and we can go above and below that sound speed climb. They're also very suitable for studying both active acoustics and passive acoustics. And whether you have one glider with multiple hydrophones or a fleet of gliders all with at least one hydrophone, they have the potential for really interesting range finding and source localization. So now I'll talk about our Slocum integration and some of the challenges there and the solutions that we found. So this on the left is sort of our minimum viable parameters. We need at least one hydrophone, 48 kilohertz sampling rate, continuous recording, onboard data storage. At minimum, we wanted a glider independent system, which would only have delayed mode data, nothing real time, and it needed a constant power supply. So some of the challenges involved with that is what board do you use? Do you choose a third party or do you design your own? What kind of hydrophone do you use? Where do you place the board? Because these gliders, as you guys know, have a solid space constraint within that aft hull and science bay. So where can you place that board and wire it so that you can have constant power delivery throughout the deployment? So first, I'll talk about our board and hydrophone selection. So we, for our first endeavor in this, went with a Loggerhead LS1, LS2 board, which had an HTI 96 min hydrophone. And so this was sort of the consensus with the collaborators on the project that inspired this development. And so this actually worked really well for us. It runs on three 3.6 volt lithium D cell batteries. And so those are, about an inch each. So not the easiest to fit into the glider, but it had its own power supply. So we didn't have to port anything from the glider itself. As for the hydrophone placement, so we had a dissolved oxygen sensor MCBH connector on that aft bulkhead. And so we had Teledyne, the amazing Dan Vian, who's unfortunately no longer with us. He helped us rewire that MCBH connector in order to use a hydrophone right in that port. And so that was great because the hydrophone was protected by the aft cowling, so we weren't getting a lot of that flow noise around it. So that ended up working really well for us. And that was on the both the G2 and the G3. As for the board placement, so this is where our solutions kind of differed between the G2 and the G3. So for our G3 glider, we had loads of space right above the main tray. And so we actually printed and designed and printed these little feet connectors that stood on aluminum standoffs. You can see it's right next to that compass section. And so that worked really well because it wasn't too tall. It stayed below that. You can see that black rectangle we sort of used as our height maximum. So that worked really well for us. And the PLA plastic and the fact that these standoffs were on these grounded copper pads kept the board totally electrically insulated from the glider, which was really important to prevent any current leakage or anything. For the battery placement, we designed and printed this plastic tray that we sat in the aft bulkhead, and there were two little screw holes back there that we were able to affix it to. You can kind of see them right right down there next to the leak detect. So we were able to attach it firmly to that and just attach these battery holders right on top. And that worked really well because then we could just run the power wires straight back to that MCBH port and not have to run those all the way up and around the tray too much. Yeah. As for the G2, we did not have an extended aft hull on this one like we did on the G3. So we had to be a little more creative here. So we actually grabbed an old Echo Sounder bay that we weren't using, and we designed this modular 3D printed system that would sit up in that bay and affix to the front. I actually got it right here. I don't know how you can see it on the camera, but the board would sit right on top, and then we had 2 batteries on one side and 1 on the other, which we had to account for with ballast, obviously, but this made it really easy to swap out batteries and just take out the battery if we need, or just take out the board if we need. So this ended up working really well for us until we got an extended hull, which we can't recommend enough in our lab. So this allowed us to fix the batteries and sort of adapt this G2 solution to be a lot more similar to our G3 solution. So you can see for the board, the hydrophone board, we put it right above the tray again with this like 3D printed adapter tray mounted to standoffs in the same way. And then on the right side, the G2 aft bulkhead doesn't have those little screw holes, which were super nice down on the bottom. So we had to get a little more creative. And so we designed this frame that all of the battery holders would screw into. And then that frame you can see right up next to the tie rod there. On both sides, it would actually screw into the main tray itself. And so that ended up being a really nice secure system and really easy to pop out and replace batteries. Yeah, so now I'm going to talk about where we want to go with this integration. So since we've been able to use it on a couple deployments, we've learned a lot about how well it works and what else we think that we might want from it. And so again, I've got our minimum viable parameters on the left, and then sort of our optimal parameters. We would want a higher sampling rate just based on some of the data we were seeing. We were able to capture a lot more at a higher sampling rate. We want continuous recording, onboard data storage, which we have, but would be nice. Could potentially integrate that with the glider, and then more glider integrated communications and timing. Specifically timing here, we had a real-time clock on that loggerhead board, but we were seeing we had some issues with the absolute timing there. And so syncing that with the glider PPS signal, what we found would be really, really helpful. And then there's always a potential, like Joe mentioned earlier in his question to Frank, for some of this data processing and potentially modeling real time on the glider would be really, really neat to see. And then also being able to do away with some of these batteries and power it directly from the glider could give us a huge space-saving advantage there. And so this is something that we're currently in the prototype research phase, looking at what would be the best, whether it's another third-party board or whether we'll be designing our own in-house board. This is something we're looking into. So now I'll talk about some of the analysis that we're able to do with the data that we collected using the system. So I'll start by talking about this study that we did. This was Office of Naval Research funded study. It was the NORSE, which stands for the Northern Ocean Rapid Surface Evolution. So this was a study we did in 2023 up in the Norwegian Sea, where we deployed both our G3 Slocum glider with this system, as well as a Sea Explorer glider, which did not have acoustics on it. So our G3 glider, which you can see that track in the top right, was deployed for about 15 days, and it was recording continuously with this loggerhead system. And there were a number of other sources from other teams in the water for our glider to hear. So some of our research objectives with this study were to see how the physical features impact the propagation in the region, as well as to determine how well a profiling glider can act as sort of a synthetic vertical hydrophone array, which I'm going to talk about in a few slides. as well as assess our glider's ability to study the multipath arrival structure sort of across this region and across bathymetry. So really a solid test for our integration system to see what sort of data are we getting here from these sources and what can we do with it. So you can see that glider track again. And one of the sources that was in the water was called the debasis source. It was a drifting source, and that's that red line that you see. And the glider track is colored by how far it was from that drifting source. So that drifting source was a mid-frequency 600 hertz to 900 hertz up chirps that were separated by 5 or 15 seconds. So you can see in that top right image, that is one 20-minute transmission from that drifting source. And it was doing these 20-minute transmissions every 30 minutes. So over 15 days, that's a lot of receptions. And then our receiver is the system we just mentioned, our G3 glider with a single hydrophone, which recorded at 48 kilohertz for the entirety of the drifting source deployment. And then there was also, like I said, a number of other sources in the water. You can see one example of that Neptune source in that bottom image. So now that we have this data from this mission, we're thinking, okay, what can we do with this? And so we've developed sort of this plot, which we're calling it profiling hydrophone synthetic aperture plot. So this is very similar to a vertical hydrophone array, except here we're saying, okay, instead of with a vertical hydrophone array, you have a number of hydrophones spread at depth. We're saying, okay, what if instead we treat every reception from this drifting source as a hydrophone in a vertical array? And so then we lose sort of that temporal resolution, but what really stands out is that vertical resolution over depth of that multipath arrival structure. So here, every individual row is the cross correlation result from a pulse. Those white lines are just where the files were. You can see in that top image, one transmission would span 3 files just based on how we set up the loggerhead to record. And so now that we have this plot, we can see some really, really cool variability in the structure over depth. So you can see some really strong arrival in that first diffuse band near the surface, but so you kind of lose that as you go down. So it's sort of a case study for this. We looked at this particular glider track during the mission, which was from blue to purple, started on the 20th at 1530, ended on the 22nd at 1800, where the glider flew about 70 kilometers. And you can see the debasis drifting source. It started right here when the glider was here, and then sort of did these circles down here. So it stayed in relatively the same area, which provided a really great grounds for a case study to see if we're seeing this change in arrival structure over this period. So this is some of the glider collected data. We have our temperature, salinity, and then from that, we can calculate our sound speed profile. And so you can see that these red lines bound that track that I just mentioned. And you can see a lot of really interesting variability in the sound speed over that time. So here I just made a plot of that synthetic vertical hydrophone array plot at a number of distances. And so you can see what we expected is there's a lot of variability over this path in the multipath arrival structure. So you can see very, very diffuse bands up here, which are likely close bottom or surface bounces. And then you can see they thin out here. And you can see some even start in the 50 kilometer. They kind of start up deeper in the water column. As you can see around here, it gets much stronger down below about 100 meters. So that's the kind of thing that we're looking for, because that can help to inform what's going on in between the drifting source and the glider and whether our sound speed measurements agree with that. So I'll talk about where we want to take this analysis. So like Frank mentioned earlier, we want to start doing some of this ray trace modeling. And so we can use this ray trace modeling using our range-dependent glider collected sound speed over this track to get a really neat model for how we expect the sound to propagate. And then we can go in and actually look at these arrival plots and see, okay, is this matching up with what we expect from the model? If yes, great. If not, what's going on there? Why is there that discrepancy? And so that's sort of the next step in this analysis. I also wanted to take a second to talk about a few of our other engineering efforts in the lab. So this board that you saw next to the hydrophone in a picture earlier, which I've also got on the right, this is an onboard IMU sensor that we put in the glider. This one was totally designed in-house using a teensy microcontroller and a couple other third-party peripherals. And so we're really excited about this one. It's still very much in the prototype phase, but we've got some success with that and some neat data coming back. And then the other one is our lab has been interested in the concept for an automatic launch and recovery system. And so Dr. Gong will be giving a talk on this at Oceans 2025 in Brest later this summer. So this plot right here in the middle sort of shows the green there. The green circles show what our deployment radius is using like local boats just from the shore. And then the blue circles are what we could achieve with autonomous launch and recovery system. And so we've spent a lot of time obviously doing a lot of glider deployments off these small vessels, but we also spent some time last summer on a sailing research vessel, the RV Marie Tharp, and found that we were able to deploy and recover the glider really well off of that vessel, but also being a sailing vessel, it gave us a lot more flexibility in our glider operations. And so that's sort of driving this. It doesn't obviously have to be a sailing system. That one in the bottom right is a concept that we mocked up for this kind of thing, but sort of having that flexibility autonomously further from shore than we can normally achieve in small vessels, we think would be a really great tool for glider operators. And on that, we want your input. So this is a QR code that'll take you to a survey asking for sort of soliciting community feedback on the operational viability of this idea and what would you as glider operators in this community want to see out of a system like this. And that's my last one, so I'll just sort of leave that up during questions. Thank you.
Cool, Jack. That was really, really cool. The former glider tech and me loved the beginning part of your talk.
Thank you.
Any questions for Jack? I will jump in again then. So on the former glider tech question line here, I see that you guys did a lot of 3D printing for mounting internally. Are you just a CAD wizard, or how did you like come up with a lot of those solutions? They seem like they like really seamlessly fit into the glider.
Yeah, so obviously a lot of iteration with that was the key. But yeah, so when I was an undergrad at William & Mary, I participated in this program that allowed me to concentrate in engineering, physics, and applied design during my physics degree. And so we learned a lot of CAD there. And so we had the opportunity to work with a lot of undergrads, specifically Fiona Gordon, who I had on the lab team page. She was an undergraduate research assistant in that program. And so we worked a lot with students at William & Mary to iterate and design these specific glider systems. So yeah, it was really great to work with them and allow them to sort of use this as one of their projects.
Cool.
But yeah, a lot of CAD, a lot of iterations.
Any other questions for Jack?
Oh, and I should, if anyone is interested in any of these CAD designs that I showed, if anyone's interested in sort of doing this on their gliders, feel free to reach out and we'd be happy to share some of those designs.
I have a question or comment. I'll just kind of jump in. I didn't raise my hand with the little icon, but in our lab at USF, University of South Florida, we use some PAM boards called snap boards by a company called Loggerhead, and they're integrated within the glider through the glider's power. So I'm not the best person to ask about these, but we have 2 engineers on our group that you might want to get in contact just to see how we're doing it here and if it's, similar to what you guys are doing or something that you're interested in. Alex Silverman and Chad Lemke would be the best points.
Yeah,
You
absolutely.
might, share ideas or something like that.
Yeah, that'd be
You
amazing.
have a-
Thank you.
Do you have a contact that
Yeah,
you can flash or?
yeah, I don't have, maybe not here on the lab website. Oh,
We can
that's
put it
not
in
for
the
sure.
chat.
Yeah,
As
I'll
well.
throw my email in the chat for sure.
Okay.
Yeah,
And
thank you.
I was interested in the IMU as well, so I might want to just follow up with you on that.
Absolutely, would love to.
Thank you. Good talk.
Thank you.
Well, barring no more questions for any of the speakers, I think we can give everybody a little round of applause and thank all of our awesome talks, super diverse talks, which was awesome. And maybe I'll just pass it back to Georgia. Any closing remarks?
Yeah, thank you. Yeah, I just want to reiterate a huge thanks to all 4 presenters. Yeah, amazing. And also to you, Joe, for moderating the session. This was really, I think, a valuable session, and I would be very keen to continue this. Again, welcome feedback or any volunteers for the next the next version. We are at time, so I'll just leave it there. But as always, please feel free to reach out to us either by my email or via Slack if you have any questions or comments. The next webinar will be in July, and we're hoping to focus on battery safety and supply. So stay tuned for some updates on that. Otherwise, have a fantastic rest of your week and a nice weekend. Thank you, everyone.